Okay, so I have started recording. Yeah, let me share my screen. Okay, you can see my screen, right? Hmm. Okay, sure. So, so today we'll be covering. So let's just touch upon what we have covered in the last week. So, we covered validation, how cross validation works in terms of practice, and how it is different from trend test split. And did some examples on cross validation. Later on, we also like understood the theory of bootstrapping, how bagging boosting works, and do some hands-on on random forests or voting classifiers like this, right? So yeah, the video is there in YouTube. So if you want to recap some part of it, you can just go there and watch. Okay. For week 8, what we'll be covering will be so today's topic are mostly these Bayesian networks. Okay. So what is or how this naive Bayes classifier works, and how, let's say, we can represent data in terms of a belief network, right? And later on, these topics are for week 8's content from the course. So what is multi-class classification, and sometimes this term also came to us, right? This multi-label classification. So what is the difference between multi-class and multi-label, and what are the kind of metrics that we use in case of a multi-class scenario? Okay, so whenever, let's say, I want to measure between multiple classes, the accuracy of a classifier across multiple classes. In that case, directly computing accuracy or directly computing any metric like F1 score can give me bias estimate. Why? Because one class may have very little samples, right? So one class might have very less number of samples, and the performance of the classifier for that class would be not represented if I just do average. Okay, if I just take average accuracy or something. So we'll cover those parts. So let's start with naive Bayes classifier. Okay, so because so this is the simplest classifier that we can build with a naive Bayes approach. Okay, so I guess you already know this, or like what is naive Bayes theorem, right? That this theorem is naive Bayes theorem. So let me theorem. So this is class probability. Okay. So this is class probability P of Ci. Then we have the likelihood, right? So what is the let's say what is the probability of a particular feature given a particular class? Okay, so it's likelihood, and then we have the evidence of that particular feature, right? Or let's say a set of features. X is a set of feature. Now, if I just do this, what would happen? We will get Ci by X, and how we can get it? Let me just break this formula a bit. Let's just create another page. Now, okay, so what we have this probability of a particular class, let's say C1, given a particular data X, right? Uh, so what is it? So if you can just remember P of A by B, right? A by B is what? P of A times P of B by A by P of B, right? So that is what we are exactly doing. This is naive Bayes theorem, where PB is what? PB is uh, for all possible is so P of, so let's say this is A1, right? A1, A1. So for all possible A's, you will just multiply the corresponding conditional probability. So P of A1, sorry, let's say AI, P of P by AI, right? We just sum all of them, we'll get PB, right? So PB is basically the evidence of a particular feature or feature set. And then this one, P of B given A, which is, if I just represent it with C and X, it will be more clear. So similarly, we can write the same equation like P of C1, right, into P of X given C1 divided by P of X, right? So how we name them? Uh, this is your what, like, this is what you want, right? This is your posterior probability. Okay, this is your class probability, this is your likelihood, and this is your evidence. Okay, so this is sometimes known as prior. Okay, okay. So so one good example would be what, just so I guess you have 1 minute. So I guess you have already done those type of math questions, right? That, let's say, I have so the standard naive bias questions, that let's say uh, uh, I have a blue basket and a red basket, right? And I have uh, let's say uh, black balls, right? And green balls. Right now, from this setup, I draw a ball randomly, right? What is the probability? So how we represent the probability? It's represented like this, right? Let's use which color I can use. Only these colors are there. Let's say what is the probability that so what are the probabilities that we can, so this is blue basket, let's say blue basket, and this is red basket, right? Red basket. Uh, so what are the probabilities that we can, like, directly compute from this setup? Probability of picking blue basket, probability of picking red basket, that we can compute directly. It's 1 by 2, 1 by 2, right? Now we can also compute, given I have picked red basket, what is the probability of red and sorry, given I have picked a blue basket. Let's say given I have picked the blue basket, what is the probability of green, right? That I can compute. It's how much? It is 2 by 5, right? Now similarly, I can also compute probability of given black ball, given I have select the blue basket. Similarly, I can also compute probability of green ball, given I have selected the red basket, and probability of black ball, given I have selected the red basket. So these are the probabilities that I can compute directly by seeing the setup, right? And let's just write them up. It's 1 by 2, 1 by 2. This is how much? This is 2 by 5. This is 3 by 5. Here it is 3 by 5. It is 2 by 5. Right? Let's just draw another black ball here so that we can have something different for the second case. So green would be 3 by 3, 3 by 6, right? So 1 by 2. and black would be also 1 by 2. Okay. Now, so what we can get from Bayes theorem? So Bayes theorem says us that okay, if I know these values, right? This value, so I can also compute what is my probability of picking, let's say, blue basket, given that I know I have picked a green ball, right? So it's like what is my probability of picking up a green ball from basket 2? It's kind of uh, so it's written as like this: given I have picked up a green ball, what is my probability of picking blue basket? Got it? So this one, I cannot directly look into this and tell, right? Right. So here comes the Bayes theorem. So Bayes theorem tells us what? I can represent the same thing with a multiplication of, see, similar P divided by BB divided by P of G. Got it? Now P of G, what is the total probability of picking up uh, a green ball, right? It is, you can compute it like P of G is equal to picking up a green ball from blue basket plus picking up a green ball from the red basket. So it's picking up a um, uh, so picking first pick, we have to pick up the blue basket, right? So pick up the blue basket times pick up and also pick up the green ball from it, right? Plus pick up the red basket, then and this is and operation and this is or operation in probability. Okay, so I can either pick up a green ball from the blue basket or red basket, but I have, after picking up the basket, I have to get the green ball, right? So now this star or multiply means it's an and operation. So these two events has to be occurred together, right? Or we can also pick up it from the red basket, and the joint event should be to pick up the red basket and pick up the green ball from the basket, right? Now what will be the probability? Let's compute it, and just interrupt me if you find any place confusing. Okay, so I think till now it is pretty clear, right? It's similar to what we have learned in our engineering mathematics as well as in our class 12. Same example we are picking. So now, what how we can compute it? Let's just do it. 1 by 2 times GBB. GBB is 2 by 5 plus is it 2 by 5 GBB? Yes. Okay. Now another is 1 by 2 times uh, GBB RBB 1 by 2, right? So these two cancelled. 1 by 5 plus 1 by 4 is equal to 20. 4 plus 5. So 9 by 20. Okay. So that is the probability of picking up green ball, right? Yeah, 9 by 20. Exactly. Okay. Now let's just put these values here. Now probability of BB is 1 by 2 and probability of GBB, it is here 2 by 5 divided by 9 by 20. We can just simplify these two will cross out. Now 1 by 5 times 20 by 9, 4. So my probability becomes 4 by 9. Okay. So the probability that I have given that I have picked a green ball, what is the probability of choosing the blue basket? this is what naive Bayes theorem looks like. Okay, so what is my equation that I have to remember? This one. Okay, now let's see how we can build a classifier from this. So we can just use the same equation when, let's say, x is a feature. Okay, x is only one feature. Let's say x is only one feature. So what is the probability that my class is C1 given I have value of the feature to be x, right? This is what classification means, right? If I have, let's say, the probability of p of class 1 given x, then I also have, sorry, class 1 given x, then I also have p of class 2 given x, p of class 3 given x. So that means what? Given the feature, I know all the probabilities of the, let's say, the classes, right? Then what I can do, I can just take whatever class has the maximum probability, right? So we can just take argmax, argument max. So whatever probability, whatever class has the maximum probability, that will be my prediction, right? Or my classification of that particular, given that particular feature x, right? So same thing applies here. So this is the equation for computing probability of class C1 given my feature x. That would be probability of C1. I can compute from the data set. I can estimate the probability of a particular class, how much, how we or how frequently it is occurring. So how we can compute it? Let's say cat. So what is the probability of cat from an animal data set, right? So I'll just take how many number of cat images I have, divide by total number of images. That is my P of C1, right? Similarly, I can also compute, let's say, the feature X means um, darkness, okay? Or let's say dark. X means dark. And let's stick to the same example. So how many times I have a cat image that is dark? That will be P of X given C1, right? So let's, if I just compute, or let's say not dark, let's say black, right? Let's say X is black. Now how many times I have a cat image that is black? Okay, and then P of X is what? How many times we have a image that has a black animal or something like this. Okay, so this is what uh, probability of black animal. Okay, so so this is how. So let's just write it properly somewhere. Okay, so in a let's say cat, dog, horse, like this. This is my possible classes. Let's say I have n number of classes. This is my possible label set. Okay, so I want to classify from this label set, and my features f set, okay, is something like uh, height, okay, weight, and then again color, right? Multiple features I have, and we can just represent them as, let's say, these are the classes C1, C2 cn, and we have these features x1, x2 xn, right? And now let's say xf, f number of features, n number of labels. Now we can represent the same, this entire, let's say the feature vector is represented as x, okay? So x is what? X is a set of x1, sorry, x1, x2 xf, right? This is a set. Now what is my probability? P of C1, or let's say cat, P of cat given X, given a feature X, given the set of features X is equal to probability of cat times probability of X given cat divided by probability of X, right? Yeah. So this is what naive Bayes tell us. Now the naive Bayes class, this is naive Bayes theorem, right? Here X can be, so let's just so P of X we can anyway compute, if I can compute this part, right? If I can compute that, and then we can just compute P of X just by like what is P of X? If I just is equal to P of X is what? Summation of Ci P of Ci P of X given Ci, right? Let's just given Ci. So what is the problem here? If I can just compute this part, then I can anyway compute this for all classes, and then this is the easiest part, right? I can always compute the probability of each class from the dataset, right? So now this probability of X is not an issue. The problem is I have to compute this, right? Uh, so let's just take it out from the equation first. Probability of X is a set, right? X is set how? It's height, weight, color, and all those features. Okay. Now, given it is a cat. So what we can write from the rules of probability, let's say, right? We can write it like this: probability of height given weight, color, comma, cat times probability of weight, color, given cat. I can even expand this part also. So I can expand the same logic, right? I can expand this component to be, let's say, another color times probability of weight given color comma cat times probability of color given cat, and I can just go on and on till I reach the last, till I reach the last feature. Let's say last feature is something like uh, let's say furry or not, right? Furry. Let's say the last feature is furry. Let's just put it here. F capital F, right? Furry, 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 and then when it will end, it will end at. So we expanded the green one here, right? So the green one gets expanded by these two. Now we just expand this one. And at the end, if I just go on and on expanding it, it will end at the probability of furry given cat. Right here, like let's say before furry, there was some something, right? So in that case, previously it will have probability of some feature S given furry comma cat, right? You get the idea, right? How we can expand my this entire probability. X is a set. How I can split them, right? So one assumption that naive Bayes make. So assumption. Okay. So this is a crucial assumption for the naive Bayes classifier. What is it? My features are independent given class. And this is very, very important. Okay, it can be asked in like in, let's say, MCQs and all. So this is the primary assumption that naive Bayes classifier make. Okay, that my features are independent given the class information. So I know it's a cat. So the height doesn't depend on any other HC or any other feature, given that I know it's a cat. Okay, so this height doesn't depend on this component, only depends on the cat. Similarly, for the weight, it doesn't depend on this component, it only depends on this cat. Okay. Similarly, here also, S only depends on the cat, not any feature. It doesn't depend. So here there is no other feature than no other conditional except the cat, right? Then only F only depends on the cat, right? So now if it doesn't depend on this, how I can simplify this? The entire this probability can be directly written as probability of age given cat, right? Similarly, I can also write probability of weight given cat for this part, for this one, right? Similarly, I can just go on and on and on into probability of C color given cat times just dot 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 times probability of S given cat, probability of probability of F given cat. I can just write this entire multiplication with all the feature components, whatever, let's say, feature set, however it is uh, organized, where the X is what? X is the set of age, weight, color, dot 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 S comma F. This is my entire feature set. So this thing, how I can write, because of the assumption that my feature sets or features are independent of each other given the class information. Okay. Now I can just write it multiplication of xi, probability of xi given cat, or given any class, right? It is, let's say, C, that I can write as the probability of what? X given C. Okay. Now, what is my equation now? So what I have to count, probability of a class, particular class Ci, given the entire feature X. Okay, X is a set of x1, x2, x3 all, right? My probability would be probability of C1 multiply of xi, probability of xi given Ci. No. Let's just do uh, let's just not write Ci. Let's just write C, any class. Okay, C. Here also I have to remove it. Given probability of x, and probability of x, what is it? It can be written as the summation of probability of Ci, and then you have probability of basically multiplication of, let's go with ij. Okay, here it is I, or let's go with j for the outer loop. For all possible labels, go with this multiplication I, p of xi given cj. Just tell me whether you understand this part or not. right? And this is what we can write it as p of x, and x is basically x1, x2, dot 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 xf up to the feature dimension. So get this idea, right? So this is what uh, naive Bayes classifier looks like. And after, so from data you can compute all of them, right? So given a particular, so how you can compute it, we will discuss. Let's just take a example data. But before that, uh, let's see how we can classify, right? So given a class C1, I can easily compute, let's say, probability of cat given my features X. Then let's say I have also computed probability of dog given my features X, right? And again, I have computed, let's say there are only three classes, probability of horse given X. Now, let's put some values here. Let's say my probability of cat is 0.1, my probability of dog is 0.7, and the probability of horse is 0.2, right? And see, if I just sum across all the classes, it will be 1, right? Because the denominator is actually sum of all the uh, like this one, right? Nominators, right? So you just put from here it is C, right? But if I just sum across it, let's say C1, C1, C2, C3, if I just sum across all the classes, the top and the bottom will be same. So it will be, so if I just sum across all the classes, probability of Cj given X, it will be 1, right? So here my probability would look something like this: 0.1, 0.7, and 0.2. Now what I will do, I will take whatever has the maximum probability. So which one has the maximum probability? Dog. So my prediction would be dog. And this can be done by a function in NumPy called argmax, which argument has the maximum value. So the first argument, second argument, third argument. The second argument has a dog class. So okay, dog. My prediction is dog. Okay. Now let's see how we can, so P of C we can compute from data that we can like that we can realize, right? That okay, what is the probability of a particular class, that we can easily compute from a data set, right? But what is the probability of a particular feature given a class? That is a bit confusing, I guess, right? So how we can do this? Let's say my feature is uh, my feature is uh, hmm, let's say my feature is rain, okay? Rain, and it's a true false column, whether it is raining or not. Okay, true false. Let's just put some data. True false, true false, true, sorry, true false, true true. Okay, and my class is actually whether I will play or not play. It's also a true false class. So let's see, if it is raining, I will not play. If it is not raining, I will play. If it is it's not play, so false. Now if it is raining, true. Now here somebody says okay, I will play in rain, okay, and then again someone says okay, if it is not raining then I will not play. So these are kind of people's preferences, okay, so it can change from person to person. And then for, let's say, the last two classes we have play. Okay, now a feature comes X which has the rain component to be false. Okay, now what is my probability of that particular rain to be false? So we can write it as like this, right? Rain having value false, right? Given, let's say, my class, where I want to predict whether I will play or not, right? My class is play, true. Okay, so what we can do to see from the this data set, I can compute this, right? So my class is true. So for all the values where my class is true, so this one, this one, this one, this one, and this one, right? Now how many time it is false? So one time, two time, two time, and how many times we have? One, two, three, four, five. So my probability would be 2 by 5. Now this is for a like let's say the same thing would work for any uh, categorical feature, right? Well, let's say your rain can also have your mild rain, medium rain, or high rain, right? Similarly, so for same as true false, you can also compute the probability of rain to be mild, even my play to be false. I am not playing. What is the probability that the rain is there is mild rain going on? Right? These things I can compute for any categorical features. Now, why I'm saying categorical? Because I am just applying counting, right? But what happens when we have a continuous column? So, for example, if I have, let's say, age or something, or not exactly age. Let's say I have what can be a possible blood pressure, right? I have blood pressure, and my class, what I am trying to predict is whether I have diabetes or not, right? So I have to predict probability of my BP. So this is for one particular feature component. I have to compute it for all the feature components and multiply it so that I have this part, right? So I hope till now you have followed how we have derived up till here, right? So BP is equal to, let's say my BP is something like 98. Okay. What is the probability that I have diabetes? So have diabetes true. Diabetes true. So how we can compute this? So this is difficult, right? Because BP can take any value, let's say 98.5. Now there may be no value in my data set that directly matches 98.5. It's a continuous column. So can anybody give us a hint what we can do? Okay, so let's see what we can do. We can just assume, or we can just model the distribution of BP to be a normal distribution. Let's just write down a data set first. Okay, so let's say my BP column is like this 50, 55, 49.3, 50.7, 81, 82.3, like this. Okay, so it can take any value which is let's say 95.5, 100, like this. And diabetes column is there, my label column, and now it has, let's say, true false values. Okay, so let's say false, 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 true, true, oh, sorry, true, false, something like this. Okay, now from this data, how I can compute, let's say there are many other values also. Okay, now from there, how I can compute this? It's also a standard uh, your engineering mathematics problem. How? Because we know that diabetes is true. I want to get where my diabetes is true. What is the probability of BP to be 98? You remember this type of questions, right? That let's say okay, so it's something like this. Let's say we there are 100 employees and uh, let's say 30 people left their job, what is the probability that a person left their job has age 65, like this. Similarly, what we will do, we just segregate the entire chunk where it is true. Let's say this is a true chunk, right? True chunk. And also we have these values, whatever, let's say we have a chunk here. Anyway, so all the values where we have diabetes equal to 2, we can compute the mean, mu, and sigma standard deviation from them, and just model this distribution as a normal distribution, right? So how we can compute it? We can just compute normal distribution of mu sigma from the data here. What is the probability that my BP is this? So so you cannot compute the instantaneous probability from a continuous distribution, right? So it will be probability of BP less than equal to 98.5 given. So let's just write it clearly. Probability of BP less than equal to 98.5 given I have this probability distribution, right? And we can just put the normal distribution, like probability mass function is there. Oh, sorry, density function is there, not mass. Density function for a quantity distribution. So what is it? I guess 1 over 2 over 2 pi sigma e to the power x minus mu by sigma square, something like this, right? So you can just put this 98 value here instead of x, you get the PMF. So the distribution till 98, no, 98.5, you get the entire mass till here. Not exactly, it's probability mass function. So you can just get the probability of this one. So to get the mass, you have to integrate from 0 to 9.8. Or anyway, you can also put this value here to get the mass at that point. Okay. So we will see how we have implemented it in code. Okay. So anyway, but if you just put that value here, that would also work. Okay. Okay, so that will give you that what is my probability of BP to be 98 exact. So if I just put, it will not be less than equal to, instead it will be equal to, but it is theoretically not sound because 98, because we cannot compute instantaneous probability from a continuous distribution. But anyway, in practice, what we do, we just put this value in that function and get that particular instantaneous probability at 98.5. Okay. Okay. So now you get how we can compute, let's say, these probabilities from like discrete as well as continuous features, right? Let's see how we can implement it in code. So okay, we have it. Can I increase the font? View. Okay, let's just open up another menu with VS Code. Okay, now here we can increase the font. Now see, here what we are doing, uh, we are taking a data set, okay, And then what we are doing, we are see these things. These are the featured columns, and then we have all the columns, and we are kind of saying, okay, it is a continuous column, this is a categorical column, this is a continuous column, so that we can choose how we can compute the probabilities for particular feature values. Okay, now label is patient. But these are some processing that we are doing. So what we are basically doing, we are trying to scale the categorical columns and all, the continuous columns and all, but that is not actually required. Okay, you can anyway uh, send in naive Bayes classifier. There is no point of scaling the data. Okay, it might sometime hurt you. Okay, if you do a, standard scalar, or just let's say a min max scalar, it might change your distribution and hurt your performance. Okay, so instead what we can do, we don't have to scale the data or anything. We can just pass it to our model. Here we are just doing some standard scale or something. So you're just making all the continuous distribution as normal, like standard normal distribution. So with zero mean and one standard deviation. Okay, we are trying to do that, but let's see. So in the model, series PR function. So what it does, given a particular column is continuous, it from the slice where we have the class match, right? From that column, that exact slices all the values where the class is what we are trying to compute, right? Uh, for that slice series of that particular feature, we are computing mean and standard deviation. Okay, so we are Okay, so we are computing mean and standard deviation, and then we are using, see, this equation, mu comma x mu comma std is equal to 1 over square root of 2 pi sigma square, means 2 pi sigma, uh, mm, uh, into e to the power minus x minus mu square by 2 sigma square. That's the equation for normal distribution given a mu and sigma, mu and std, mean and standard deviation, right? So that we are using to get the probability mass for that particular feature value is given x, right? So whatever feature value you pass during prediction. Okay, so you pass a value, you get the mean and standard deviation from the data, compute the probability. Given it's a categorical feature, what you do, you take the entire slice where that value match, right? And then compute how many times a particular the value what you are trying to do, right? So let's say how many times that I you have that category match. So let's say my uh, feature has a value of true. So how many times true occurs given all the other like all possible feature values, right, for that particular column. So I is how many times my value matches. You see here we are also matching with the value and also matching with the given label, right? Uh, and then just take what is the total number of possible values if the class match, and then I by n. So this alpha and alpha k, this is what is Laplace correction. So what is it? It is actually given a particular value doesn't exist in your category, you just add 1 and divide it by 1. So in both denominator and numerator, you add 1. That would not produce probabilities of 0, right? It will not produce 0 probability. So it will not uh, like hinder in the classification process. It's just 1 over total number of values plus 1. Okay, so we'll see in the slide we have content for this one also. So what it basically does, it doesn't allow any 0 probabilities to occur. If a particular value doesn't exist for a categorical feature, it will not let the probability to be 0. It will be 1 over some value, some small value. Okay. Now for predicts, so see, this is the denominator p of x. Okay, what we are doing for all class probabilities, we are trying to just compute the probability and just multiply it. So probability times this. So probability is what is it? No, it is the nominator. Okay, so P of L times P of X is equal to P of L times P of X1 given L, P of X2 given N and all. So P of probability of a class, we can get it from the data, and then we just multiply across all the features, all possible values. Okay, that is the probability of the nominator. Now, in case when we're predicting, right, given a particular X, what you are doing, we are calculating the nominator divided by sum across all the nominators. So that would give me the denominator, right? And we are adding it for the particular class, the class and its probability. Okay. So in prediction class, what you're doing, we are taking the particular class that has maximum probability. So it's actually sorting in reverse. So the first class would have the maximum probability. By default, Python sort it as a increasing, so ascending order. So doing this reverse equal to true means it will be sorting in a descending order, and taking 0 0 means it will take the 0th class which has the maximum probability. Okay, evaluate and these functions are not necessary. So get the idea how we can implement this in real life. Okay, so this is how it is implemented. So let's just go and try to code it. And let's just also go over the slides once, just to refresh all the content till now. So naive bias. So it's this equation. Okay, so it's this equation. What we are doing for all the classes, we are trying to predict their probability and then taking argument max, whichever class has the maximum probability, we will take that class as prediction. Now for naive bias, X is a set of features, right? So the input feature vector is basically comprised of values from multiple features, right? So we can represent it by a by this multiplication operation. Why? Because it is an assumption of the naive Bayes theorem that my features or feature components are independent of each other given my class, right? So I can do this. Next, I can compute likelihood to be likelihood can be computed as multiplication of all the possible values, and I have shown how we can compute this P of xi given C1, right? If it's a categorical feature, we just take all possible x1 values where the C1 matches, and then take the probability of my given x1 over all the x1s, right? And if it's a continuous value, we just take mu and sigma from that segment and then compute what is my probability of this value given that mu and sigma, right? Now to estimate this, we can see here we have also written that we can just evaluate a particular value given a mu and sigma with this equation, or if it is a categorical value, then we can just do counting how many times this value occurs on the entire data where C1 matches. Now, avoiding zero probabilities, we have shown that okay, it's a multiplication operation between all the feature components. So if one component becomes zero, let's say it's a categorical feature and it doesn't have any feature value to be, let's say, small. It has only medium, large, and very big. Okay, it doesn't have any value for small. So if I query it with small, then it will get a 0. 0 divided by the entire data where C1 is, let's say, cat, right? So that small would have 0 count. So 0 divided by entire value would be 0. So it can cause zero probabilities. So it will basically collapse the entire computation, right? So to get rid of that error, what you do, you just do this Laplace correction. You just add +1, and in the denominator also you also add +1. Okay. So 1 divided by some big number would be there. It will not be 0. It will be very small number, but not 0. Okay. Okay. Now example. Let's try to code an example on this. And then we'll go for the Bayesian networks. So Bayesian network is something very interesting. Okay. So uh, it's also known as belief networks. Uh, Okay. Source. So this is week 8. Okay. So here I have a data set. This train Bayesian.csv, and what it has, let's just see the definition. So it has uh, whether it's a patient or not. Okay. So it has it's such age, gender, something. These are kind of like this biological like your physiological measurements and all. Okay, your protein, total proteins. So what is it? The dataset content for 416 liver patient records with 160 non-liver patients. The dataset is collected, for example, northeast of Andhra Pradesh. India is present in the label column used to divide into two graphs, whether it's he is a liver patient or he or she is a liver patient or not. Okay. So these are some features that we can compute to check whether someone has liver disease or not. Okay. Okay. So let's just copy this. Let's just copy it here. So import and does as PD. PLT. Let's just import these libraries for now. So df is equal to pd dot read csv and train Bayesian.csv, right? Now what is df? This one. This is df. Now for the gender class, we have to make it categorical. So you just do a mapping of dictionary, and the patient is already 1 and 2. So you can just make it 0 and 1, right? So two things we have to just change. So this gender has to be gender map is equal to female. Let's just put female to be 1 and then male to be 0, right? And also is patient EAT or patient map. It's currently 0 and 1 and 2. Okay. So let's make them 1 to be, so 1 to be cast as 0 and 2 to be cast as 1. Okay. So TF gender dot gender map. This is how we get the data. Just put it back in the same column. Copy. Now that column is now 1 and 0s. Okay. And is patient, that we have to also just copy this and is patient, right? So we have managed to process the data. Oh, is patient is a string. So these are strings. Oh, still it is nan. Why nan? Oh, so okay. So we are doing gender map, patient map. Maybe it's not strings now. Yes, it should be 1 and 2. 1 and 2. So let's just read them. And okay, now we have zeros and ones. So we processed the data, cleaned it, right? Let's just remove the drop now. Let us remove any irregularities with the data set, right? Which has missing values or something. Now let's just do train test split for now from sklearn dot model selection. It now train test. Go there and copy this entire code here. Now df and y. What should be your df and what should be your y? So df is this. So this is y, right? See? So I can just do df dot drop column to be this patient. So just drop that column, that becomes my x, and y would be that column itself, right? So df dot this run x test y test. Fine. Okay. So now from sklearn dot naive Bayes import nb Gaussian nb, okay, or multinomial nb. You see this? These are categorical NBs, Gaussian NBs, or anything, right? So let's just go with Gaussian NBs. So it tries to estimate all the features to be normal, I guess. Gaussian NB. So what it assumes. See, naive Bayes classifier for multivariate Bernoulli model. So it assumes the models to the data distributions to be Bernoulli categorical features complement, okay, multinomial models. Anyway, so for Bernoulli it is, so for Gaussian it assumes the data distributions to be Gaussian. Okay, so what we can do instead, let's just go with Gaussian for now, but it can be like mixed also. So for example, in my implementation from scratch, what I did, I specifically pass which column is which, right? Whether it's a continuous column or it's a categorical column, right? And based on that column type, I can compute that probability differently, right? I can compute with normal distribution or with just counting. Okay, but here Gaussian would assume that okay, all my columns should be coming from normal distribution, and why I am taking Gaussian, see, from this table, all my columns are mostly continuous. Only one, this gender column, is categorical, right? And I don't think that gender would have too much impact on whether he's a or she is a liver patient. So just treat it as a Gaussian if you want, or just drop it. Let's just drop it for now. Okay, let's just drop gender. So because it's a categorical, but we are still processing it as a Gaussian. So let's just drop it. So here, so let's just read it again. Drop. So now X doesn't have the gender as well as the label. See, only age and other things. And Y has the label, whether it's a liver patient or not. Again. So now in B, what it doesn't take anything. my model dot fit xtrain ytrain. It's fitted. Now how I can compute its accuracies and all, I can just copy it from, yeah, from here, right? The function we use to evaluate all the classification and everything. Yeah, predict on train. So my training prediction is 52%. Okay, and my test prediction, let's just go and copy the test part. My test prediction is 58%. So pretty good. So if I can predict with 59%, almost 60% accuracy, whether a particular person has liver disease or not, it's good. Okay, so let's just add gender now and see whether it can improve my model performance or not. No, it doesn't improve significantly, right? So just uh, not take it as a feature. You can just also remove this map. Okay, fine. So what we can see from the confusion matrix, we can see that uh, it's it's actually 0 is getting classified as 1, right? So if I just plot the testing confusion matrix, so one thing is very important for a medical domain uh, confusion matrix, right? If I just do a plot G1 SNS. So this is, and what is 0 and 1? 0 means no patient, so label. Can I set the label? Can, I guess. X tick, Y tick labels, right? Labels is equal to. So 0 is what? 0 is not patient, and 1 is patient. If I just do this, okay. So I have to also mention the Y tick labels. So this is my okay. Now also one thing I have to annotate. Yeah. Now see this. I can also create not keyword arguments. Font size to be 22. Okay. Now see this. If I am not a patient, okay, I am classified as a not patient 51 times, and I am classifying it as a patient 76 times. So that means my model is sensitive towards classifying whether the person is a patient. Okay, so even if you don't have diabetes, like don't have liver disease, now my model is prone to predict you have liver disease. Go check with doctors, rather than when you are a patient and it is predicting that okay, you are not a patient. So my model is safe. Why? Because it can misguide healthy people to go and check with doctors for liver disease, but it can correctly classify, or most of the time it can correctly classify whether a particular person has liver disease or not, right? So if a particular uh, person has liver disease, then he will not likely be classified as you are fine, go chill, okay, like this. So it is more prone to predict you that you have disease, go check with doctors. So that means my model is safe. It will not hurt anyone. And see here, right? This one. The class 1 has higher F1 score than class 0. So it can tell, okay, you have diabetes, and then you go check with doctors, find out that, okay, no, I don't have, no, not diabetes, I don't have liver disease. But if you have liver disease, it will definitely tell, okay, you have liver disease. Okay, and it's most of the time it is true. For 65 number of times, it is 63% of the time it is true. Okay, so you got the idea, right? Okay, so for medical models or anything like that, this property is very important. So even if my model overall model accuracy is good, but my patients are sometimes more times classified as not patients, then that model is bad. So for example, if I had a model something like this, let's say 100 or let's say 100, then 26. Let's say here we have 110. So here, let's say we have something like 123 or something. Okay. And at the bottom, we have, let's say 10, comma, 55, right? So this model is actually bad. Why? Because it classifies 10 people who are patient. It classifies 10 people as they are not patient. Okay. But it correctly classifies the patients who are not liver disease patients better than this model, but this is not safe. This is not a safe model. Okay, people would go for this model with they would prefer to use this model instead of this or medical domain. Okay, or which has very like let's say impact on people's life. Okay, so then this false positives are okay, but false negatives are not okay. Okay. Okay, so this is what naive Bayes classifier is. Uh, you will share the code. I can also share you this code that I did in during when I take the course here. Okay. Now go with this one. So now went out, just connected now. Okay. So what is Bayesian networks? It's a way to represent dependencies among different features. Okay. So let's say given it is rainy, what is the probability of there will be mud in the road? Something like this. Okay. So the features, two features could be rainy and muddy, right? So what is the probability of so these two are related, right, with each other. So the rain directly influence whether it will be muddy in the road or not. So that type of relationships, those complex relationships that I'm talking about, right? It can be multiple variables that can influence a particular phenomenon, right? Um, these relationships can be captured with Bayesian networks. And what do I mean by captured? It's basically how probable a particular event is based on what are the other like on which events they are dependent on, right? So, for example, a good example is here. What is the so y is dependent on x. So x is an independent event. Now, what is the probability of y given x? Okay, so y would only happen with certain probability of x. Okay, so if x happens, there will be a certain probability that y will also happen. So similar to the previous example, there will be mud in road given there is a rain before it, right? That type of relationships. Now, for example, here, right, rain and wet grass. So probability of rain is 0.2, and then probability of wet grass given rain is 0.8. Probability of wet grass given not rain. So it's if it is not raining, then it is 0.3. So we can represent what is the probability of um, rain and wet grass, something like this. Okay, so if I have these probabilities, if I can compute these probabilities from my data set, right, I can represent probability of rain as well as wet grass together. Okay, so we'll see how we can represent them, and see there are these type of possible possible dependencies, right? So let's say z is dependent on y, and then x is dependent on z, and now I have to compute probability of x, y, z given occurring together, right? So in that case, what I can do, I can just see y is a independent, right? So probability of y multiplied with probability of z given y, and then x is dependent on z, so probability of z given x. So if I know these probabilities, I can from this Bayesian diagram. So this is kind of a Bayesian relationship we are representing it as a diagram. Okay. So z is dependent on y, x is dependent on z. So if I want to compute the joint probability of x, y, z, and see, this is important because in the final exams or in the assignments, there can be this type of diagrams where all the probabilities are mentioned and you have to compute some joint probability of, let's say, y and z happening together, okay, or x, y, z happening together. You have to compute those probabilities, and now to compute those probabilities, you have to see the dependencies, based on that multiply the which probabilities have to multiply to get that joint probability. For example, here I want xyz to be computed, joint probability of xyz, right? Then see, y is independent, so probability of y times. So it's a joint, so it will be AND operation times um, z, probability of z. Z is dependent on y. So given y happened, what is the probability of z also happening? So y is given, z also happening. Now given z is happened, what is the probability of x happening? Z divided by y. So this diagram I can compute here like this. Now, if I have to compute probability of y and z, that's my asked question, right? What is the probability of y and z to be happening together? I can just multiply probability of y times probability of z given y. Okay. Now, if my graph looks like this, that x and y both depends on z, then the probability multiplication is different. See, probability of x, y, z, that z is independent, so probability of z times probability of x given z, probability of y given z. Okay, so given a graph, given a Bayesian network that represents relationship between, let's say, phenomenons, right? X, Y, Z, these are events or phenomenons. Um, and they are sometimes also referred to as, let's say, the features, right? The individual features. Let's say that rain feature depends on mud feature, or it depends on whether the road is slippery or not, right? So you can represent the relationship between feature components with a Bayesian network like this. Okay. Now this is another Bayesian network. See, cloudy, that is depend. So if cloudy, so whenever rain is happening, right, there will be cloudy before it. So if I know the so cloudy event directly influence rain, rain influence wet grass. So this is an example of this type of relationship in my feature space. Okay. Now another another represent could be cloudy, so it can trigger sprinklers or it can trigger rain. So given it's cloudy, sometimes sprinklers can be triggered, Okay, or it can also cause rain. Okay, same. So example scenarios of this. Now I can have probabilities of all of these. So these probabilities I can compute. Okay, and based on these probabilities I can compute what is the probability of cloudy and rain, what is the probability of cloudy given sprinklers are happening. Okay, or what is the probability of it is cloudy and sprinklers happening together. Okay, or what is the probability of rain and wet grass, what is the probability of cloudy, rain and wet grass, like this together. Similarly, this type of relations can also happen that two features influence a particular feature z. So here P of x, P of y, those are independent, and then z can be dependent on x and y both. So P of x given z, x comma z, right? So those can be computed as see we can just, if I want to compute all probabilities, I can just P of x, P of y, P of z given x, y, and P of x, y is, but they are independent, so we can just multiply them, right? And use the Bayes theorem to compute P of z given x, y. Okay. So P of x, y given z, and then we just do the same Bayes theorem approach for computing P of z given x, y. Okay, and these questions may come. Okay, these questions are very common in exams and all, that you have this type of a graph, all the probability values are given, you have to compute a particular joint probability, that okay, what is the probability of cloudy, sprinklers, wet grass. You have to just compute the joint probability of cloudy, comma, sprinklers, comma, wet grass. So what you have to do, you have to traverse this path, right? So my probability of PC, RS, P of S given C, and P of W given S. Okay. Um, Again, so in this path also it can come. So you have to also know the probability of this path, P of S given W given S. Okay, or if it is not there, so you have to compute it. Okay. So for example, if I want to jointly compute all probabilities, I can just multiply 1, 2, 3, these probabilities only. So cloudy is a independent event. It triggers sprinklers or rain. Times it can both of them can cause wet grass, right? Okay. So the formula for any computing any probability from a Bayesian network is that particular event given all of its parent events, and you just multiply them across the entire network. Okay, so a particular joint event in a Bayesian network can be classified as the multiplication of that event given all of its parent event, and it will be recursion until you reach the independent event, right? There is no parent of a particular event. When like, independent events are those which have no parent, right? So the recursion would stop there. So for example, here uh, wet grass times their parent. So wet grass given their parents, and then their parents would be this one and this one. So P of S given C, their parent, P of R given C, their parent, and then cloud doesn't have any parent, P of C, like this. So this is the like the joint probability computation formula for a Bayesian network. Okay. And now the naive Bayes classifier that we learned earlier, that is a special case of a Bayesian network itself. So why? So all the features are independent. So the graph looks like this. Okay. So from these Bayesian networks, we can also compute Z given XY. Okay, just the reverse. So for going downwards, you just do multiplication, joint multiplications, right? And if you just go upward, you can do Bayesian theorem, Bayes theorem, right? So in naive Bayes classifier, the graph looks like this. There is a particular class which influence all the features. Okay, and that you can just compute with this approach, Bayes theorem. Now another there is another this kind of representation for Bayesian networks, which is a specialized representation, I would say, and these are hidden Markov models. Okay, so there is a start state, so it is used to handle time series data, and it represents the intermediate state changes and what is the observed. So there are two types of states here. Here you see there are independent states and dependent states, right? Here uh, you kind of have two type of states. One is hidden state and observable state. Okay, so there is a start probability start based on from that start state you can transition to multiple hidden states. Okay, and those hidden states will basically transition among themselves based on transition probabilities. See, here we have marked all the transition probabilities. So given what is the probability of transition to rainy given you are at sunny? So it's P of rainy given sunny, something like this. Okay. So we represent also, it's like, so the self loop is given rainy, given like probability of rainy given rainy. So it is the probability of rain continue, like being rain continue to the next timestamp. Okay. If it is a hourly data, if currently it is raining, what is the probability of raining in the next hour? Something like this. Okay. So these are known as transition probabilities. You can estimate those probabilities from the data. So for example, rainy given rainy, what is the number of instances where it rained for two consecutive hours? Or what is the probability of raining from two consecutive sunny being weather being sunny for two consecutive hours, right? Similarly, what is the probability of moving from a sunny hour to a rainy hour? Okay, so you can compute these probabilities from data. Okay, and there are these. Okay, so there are these observable states as well. So observable states means what is, so these things, these hidden states are represented as features. Okay, so features basically represents these hidden states, and observables are basically what you are trying to predict. So whether it's a dry grass or a wet grass. Okay, so there are probabilities for those two, right? So given what is the probability of a wet grass given it was raining, something like so. These are kind of these are known as emission probabilities. Okay, so given a state transition between the hidden state, what is my emission probability of the label? And it is basically used to represent time series data. Okay, so each time you start with a timestamp, you start with that starting state and you transition and go to an emission state or observable state. Okay, so let's say if I want to process a time series data, okay, for let's say I want to process 10 data points and then predict what is my label, that can be done with this. Okay, or each time, let's say if each time I see some state, I just go to an emission state if I want to just represent the next timestamp data. Okay, so this is, I guess we can discuss this in the upcoming lectures also. But anyway, so today's topic was basically how we can represent this naive Bayes classifier as well as this type of numericals, and they're very common in any exams. Okay, so to practice them. So if we have a particular let's say configuration of features and you know all the probabilities, and one thing is, if there is some question like this, you will be given all possible, like say all required probability values to compute any or whatever that is, like whatever is asked in the question. Okay, so if you have to go back downward, you have to just do multiplication. If you have to go upward in the network, you can do that Bayes theorem calculation. Okay, so for example, probability of R given C we have, right? If I want to compute probability of C given R, I know the probability of rain, probability of sprinklers. I can just do the that probability of C we know, and just do Bayes theorem, that equation P of C given R equal to P of C times P of R given C, P of C given P of C given, sorry, the equation would look like this, right? So in this graph, I want to compute, and these things, if it is not mentioned, you are supposed to compute them. So draw. So my diagram is this: P of, this is C, and then here you have S, and also you have R, right? And what we know, probability of R given C, we know. We just get it from the data. Probability of S given C, we know. Probability of C, we know. Now probability of S, we know. From the data, we can get these things, right? What is the probability of sprinklers firing, or what is the probability of rain? That can be directly computed from the data. R we know, right? Now, if I want to compute probability of C given R given C is okay. We can compute it from data. What is the probability of R given C? Sorry, C given R. We can just use the Bayes theorem, right? So probability of C, probability of R given C divided by probability of C. So if a particular probability is not given and you want to, so let's say there is a graph like this. So if a particular probability is not given, you are supposed to compute them. So let's say there is a graph A, B, and then let's say there is a D or something. Let's say E, F, and there is a D here, right? Now they are given probability of D, probability of F. So sorry, the arrows are different. Yeah, like this, right? Now probability of D is given here. Probability of D given B is given. Probability of D given A is given. Probability of D is given, fine. Probability of F given D is given. Probability of E given D is given, right? Now you are asked to compute probability of D, uh, probability of D given A, B, C, and D. Okay. Uh, let's say, let's not go this way. Let's just say you are supposed to compute probability of E given, sorry, probability of E and F occurring jointly together. Okay. So probability of E given D, probability of F given D, and then probability of D. Okay. And then probability of D is also, so probability of D can be computed as, it is also dependent on A and B. So probability of A, AB, probability of A, probability of B, like this. So if you want to compute probability of E and F jointly occurring together, we have to go across all this. So we have to compute this one. Other things we can just get it directly, right? Probability of D given AB, it's a bit hectic. Let's say we have to compute it somehow. Okay, let's see whether we can compute it. P of D given A comma B. A and B are independent. So that means we can write it as probability of D, probability of AB, sorry, AB given D divided by probability of AB. Now A and B are independent, right? So what we can do, we can do probability of D, that we can compute it from the data. Probability of A given D. Now see D, A given D. So A is actually independent, right? And AB are independent. So this becomes probability of AB actually. AB doesn't depend on D. So it becomes probability of AB divided by probability of AB. They will cut probability of D. So probability of D we can compute from the data. So this entire thing from the graph becomes probability of D. Okay. So my computer, so if I just know this thing, know these all values, I can compute probability of E and F occurring together. Just multiplying E of D, F of D. So why I didn't do P of D directly? Because from the formulation, from this uh, equation, right? From this equation, what we know, we have to go by the parents. So I just write, firstly, I write, okay, now this would be my parent for D, A and B, and then their parents, right? And A and B doesn't have any parents, so that's fine, right? Now what I prove here, now in this type of a scenario, if A and B are independent, then it will become P of D. Okay. So if I just have these values, P of A, P of B, P of D, and these two, I can compute P of FE directly. Okay, so I guess it is clear. Let's just do one example or something that will be more clear. Y. Now see, this is how we can represent relationships between features. Okay. Hmm. Yeah, like this here, right? So economic environment, special funding, good job, promising career. So economic funding, that is influencing special funding and good job, and then they are impacting the promising career, right? Now, what is the causal so let's say I want to compute what is the probability of economic environment given I have a good career, right? So this entire chain I can compute by multiplying with this path. Okay. So it can be computed as probability of economic so probability of economic environment times probability of C by E divided by probability of E. C by E divided by probability of C, right? And that I can compute by just multiplying these probabilities together just by using name like Bayes theorem. Okay. Similarly, and these type of questions are very common in exams. Here also, whether it is no, probabilities are given or not. Uh, mhm. Yeah, so these are some yeah. So these are some kind of real world Bayesian networks on some data sets. So how each particular feature is dependent or influencing other features. See here, right? Here they're kind of representing all possible probabilities. Now from these probability values, we can compute joint probability or let's say conditional probability of a particular feature given a particular feature. Let's say I want to compute probability of this dementia given somebody has a stroke. Okay, so that I can compute by directly like seeing here. Okay, see A is the not the true value and S is, so these are all categorical values, true and false, right? So A and S, these are like positive and negative values. For if somebody has multiple values N, S, D, all their possible all their possible values N, S, D, N, S, D, like D bar like this. Okay, and what are their probabilities? We can just compute any possible path. So let's say my age is medium. Okay, and what is the probability of stroke, dementia, and in a medium age? Okay, so I have to pass through this path. So the joint probability of D, S, and A, right? So probability of D times so probability of A times probability of S given A times probability of D given S. That would be my answer. Okay, so any questions till now? So so I guess there will be questions similar to this in week one's assignment. See this one. So figure below shows a Bayesian network with 9 variables, all of which are binary. So all of them has binary values, and these are the kind of like the which of the following statements are true for the above Bayesian network. Now from this graph you have to tick mark which particular probability computations are following the right path. Something like this. Yes, okay. Consider the following data points: 20 buckets phone, 30 mid-range phones, 20 high-end phones. Okay. Consider a phone with 2 SIM card slots, 2 NFCs, and all. Mid-range, high probability. Correct ordering of phone type for the highest to lowest probability is what? Okay. So, what is the probability of a particular phone which has the highest probability? These are counting problems. Okay. Okay. So one problem is from the graph. Others are counting problems and all. I guess knife bias problem would be there somewhere. Okay. So let's move on to other topics. Okay, now we have multi-class classification and multi-label classification, right? So what is multi-class? So if you have multiple class that that cannot jointly occur. So that means the classes are they cannot jointly occur. Okay. Okay. So multi-class means they cannot jointly occur together. Oh, sorry. Okay. So what do I mean by jointly occurrence? Let's say one particular image, right? Let's say IMG cannot be dog and cat together, right? There is no image that represents a dog and cat together. If it has only one animal in it, right? It can have two animals that represents dog and cat together, but assuming that we have only one animal in the picture, animal cannot represent dog and cat together. That is what we mean by class, multi-class. Okay, so let's say dog, cat, and horse. The same example we took earlier. So it's a multi-class scenario when you have multiple classes to choose from, but they cannot occur together. Okay. Now, what is multi-label? It is a kind of a more uh, kind of general scenario when a particular instance can represent multiple classes together. Okay. So what is an example? Example could be, let's say, a particular road junction. Let's say there is an image of a road junction. Okay. Road junction image IMG. It can represent a turn, a signal, and a bus stop together. Let's say there are other two classes also. Let's say another class is let's say whether it's an ad hoc stop. Ad hoc means whether bus stop there on people's hand, right? They just show their hand and that bus stops. Whether it's an ad hoc stop or whether it's a congestion, right? And see how many possibilities are there. So a particular road junction can represent a turn. Let's say the road junction is like this. Okay, so this one represents a turn, right? From the image, I can also classify it as a turn. So there are always signals here and there in road junctions, right? So I can also classify it as a signal, but it might not be an ad hoc, right? Um, it may or may not be a bus stop. Let's consider it is not a bus stop at a signal. And let's say there might be some congestion time to time. So there can be also classified as a congestion. So now see, earlier the prediction should represents only one class, right? It should not represent horse or cat together or horse or dog together. Now here in this classification scenario, it can represent a particular input can represent multiple classes, right? So these are known as multi-label scenarios, and the above one known as multi-class. Okay, so what is the approach for a multi-label and multi-class scenario? You just see the general approach is, let's say there is an X, switch to, there is an input X for a multi-class scenario. You give it to any model, right? Now what it gives you as an output, I'm talking about general. Okay, it's applied for neural networks. It applies for any machine learning model and all. Okay, so what it gives you, it gives you probability of class C1 given X, probability of class C2 given X, probability of class C3 given X, where probability of class Cn given X. Let's say there are n classes, and the assumption is summation of all these probabilities Ci given X, if I just sum over I, would be 1. So that means the entire output represents a joint probability distribution. And to do that in neural network, what we do, we just use this softmax activation that converts our neural network to a joint probability distribution, right? Now, this is a multi-class example. Now, multi-level would look like this. You use like similarly, you give an input X. There is this model, right? It also outputs probability of class 1 given X, probability of class 2 given X, dot, 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 probability of class N given X. Now, the change would be this value is independent of this. Okay, so this would range from 0 to 1. Now this would also range from 0 to 1. This would also range from 0 to 1. So the probabilities are independent of each other. Okay, and by summing them across I, probability of Ci given X, we can have a maximum value from, or let's say a range of value from 0 to N, because there are N classes, right? We are just summing over N actually. So each can vary from, say, the difference you can see from here, right? It is yeah, so it is for the multi-class instance, it is summing up to 1, and for the multi-level instance, it is uh, summing up to N. So there are N independent probability distributions, and to do that in neural network, what we do, we use the sigmoid activations in the neurons. So softmax, what it does, it basically like divide the entire distribution with a with kind of that evidence function. Okay, so P of X, that thing is divided and just make the entire distribution as JDP. But here, in case of a multi-level instance, it is not normalizing them. It is a independent probability distribution, we can say. Okay, they are independent from each other. Okay, so this is what multi-level and multi-class means. And to evaluate, let's say to evaluate multi-class, so multi-class. So we are just only talking about multi-class now. Multi-level, we can just evaluate. We'll just talk about it later on, how to evaluate multi-level instances, if we can find some good examples of it. Okay, so for multi-class, there is a good metrics called accuracy, SCU, accuracy, recall, or let's say precision, as well as F1 score. These things we can use to measure the performance of a model in a multi-class scenario, right? So one thing is very important in this case. So in a multi-class scenario, there can be a data distribution that looks like this. So let's say a pie chart, right? And yeah, like this. Let's say there is a class C1, a class C2, a class C3, and C4. C4, right? Now see, the C4 has very less amount of data, right? It's just a pie chart. C4 has very less amount of data. Now, if I consider the accuracy of C1 to be same as C1, C4 to be same as C1, C2, C3, then I will just, because there are less number of instances, it will have less impact on average accuracy, right? So for to deal with that, there are actually 3 ways how you can calculate accuracy, precision, recall, and F1 score. Okay, so you can compute. So accuracy can be directly, because the accuracy is not which kind of incorporates weightage. Okay, so it's F1 score, precision, and recall. Accuracy is directly computed. How many times it is predicting correctly, or let's see whether it has accuracy, the weight to weight component or not. So basically there are three methods: micro, micro average, um, macro average, and weighted. The general method we think about is micro. So it's not considering any imbalance in the data set or anything. Okay? It's just taking simple average across all the classes. Okay. Now macro is different. Macro treats all the classes to be uh, to have same impact on the accuracy. So let's say if I have some class which has very less number of instances in the data, so in that case my macro would be a better choice because it will also prioritize that class more, which has less number of data. Where in case of micro, it will be not considered that much because obviously it has less number of data points, right? Now, weighted is something different. Weighted means it will consider the classes that have higher number of instances more than the classes which has lower number of instances. Okay, so the accuracy is weighted uh, by the number of samples it has, or let's say fun score is weighted by the number of samples it has. Okay, so based on which type of evaluation you are doing, whether the minority class has more influence on your let's say model safety, or you want to prioritize the minority classes. In that case, macro is the best choice for averaging, whereas weighted and micro, they are also micro is generally the default is micro. And if you want to also, let's say, prioritize the classes that are more frequent, then weighted will be a better choice. Okay. So based on your use case scenario, you can either choose for micro average, macro average, or weighted. And where you have to choose them, let me show you in case of, let's say, earlier what we are doing. For all our practices and all, what is the, yeah, here, right? See this function, we have take average to be weighted. Now, see, accuracy doesn't have that type of a average part, right? Because accuracy is plain accuracy. How many times you tell correctly, how many times you cannot. Now, this precision recall F1 score, they have this average weighted uh, thing because it gets computed class wise, and that class sample size is important. How uh, how much it will impact on the entire metric. Okay, so you see here this average binary. So let's see where what are the values you can put there. So micro, macro, samples, weighted, and binary. Okay. So now see what they exactly means. The parameter is required for multi-class slash multi-level targets. None, if none, the scores for each class are written. Otherwise, thus determines the type of average on the data. So if I just put nan, it will return scores for each class, particular class. Recall for each particular class C1, C2, C3 like this. Binary, it only reports results from class specified by Bayesian level. This target applicable only if so the binary average is applicable if it is a binary classification task. Okay. Micro is applicable for a multi-class instance when calculates metric are varied by counting total true values by total false values for a multi-class instance. Okay. Macro calculates metrics for each level and find their unweighted mean. Okay, this does not take label imbalance into account. Okay, and weighted. So basically, all the class instances would uh, have the same impact on the computed metric for a macro average. Okay, weighted. So calculate matrices for each level and find their average weighted by support. So the number of true instances for each level. This alters macro to account for level imbalance. So if my data set has level imbalance, it considered that level imbalance in the metric. Okay. Okay, only multi. Okay, samples is some metric which is only valid for multi-label classification. Okay, so samples mean for, I guess, calculate metrics for each instance and find their average only meaningful for okay. Okay, so it computes those matrices for each instance, because a particular input can be classified as, let's say, 2 or 3 classes together, right? Okay, so this is the entire how we can basically have different averaging rules based on whether you are, it's a multi-class, multi-level, or a binary classification task. So by default, we go with average, but based on whether you want to prioritize the binary class or not, that varies. The macro is sometimes also used. Okay, so macro basically prioritize all the classes similarly, whereas weighted factor is with the number of samples you have per class. Okay, yeah. So I guess we completed the entire thing that we want to cover today. Okay, so any doubts? Any doubts till now? And one thing I should mention is this: these things are taken from one of the professor's slides here. So he has open source his slides. I've taken the slides, taken the components from his slides only. So any questions? Okay, so okay, so I will upload week 7. So what is the deadline for week 7's? So week 8's assignments? It's on 19th, right? Week 8 and week 7 from when it is? Week 7. It is on 12. So I'll upload on 13th, week 7's assignment for the previous run. And week 8, I will upload it after 19th. Okay. So you can also see them. Okay. I guess we can close today's call. And if you have any questions, you can just put it in the WhatsApp group itself about knife-based classifier or Bayesian networks. Okay. Okay, guys. Let me stop sharing. Stop recording.